Hey, good morning. Short little video this morning about the path that I'm on to develop energy storage. I've got a little outline here that I'm going to share with you on the whiteboard. This is kind of my energy storage map, the kind of thing that makes things a little bit clearer, at least in my mind, of where I'm at, where I'm going. We're basically ending up with a carbon-carbon supercapacitor, and you'll see how that evolves through my thought process here. But I thought it might be useful for a lot of the viewers out there that are thinking about developing their own energy storage, whether it's hydro or chemical or mechanical. I'm really focusing on the electrochemical side of things. We're not going to build a water tower to do any hydroelectric storage. We're not doing chemical storage, whether it be in hydrogen or fuel cells. We're not doing mechanical energy storage, things like flywheels, giant springs, that sort of thing. We are focusing on the electrochemical, which I guess covers a very, very wide spectrum on its own, everything from capacitors to batteries and all the hybrid versions and everything in between. So that's a lot of different types of chemistries and variations. We've narrowed it down to a path here that for my goals, which are keep things simple, keep things low cost, albeit maybe not as energy dense as, let's say, a lithium battery power wall, but certainly much lower cost. Let's say we're at 1/10 of the cost, and somewhere as a goal or a target in the range of a fourth to a half of the energy density, whether you are measuring that density either in volumetric or gravimetric or even just in surface area of the batteries. But that's the target. Here's the goal. So let me put a few things up on the whiteboard and I'll show you kind of where my thinking is at. So when we talk about electrochemical energy storage, okay, we can divide that into three areas. Let's over here talk about capacitors. Over here we've certainly got all the various forms, versions, variations of batteries, and in the middle kind of a mix of the two depending on how you package your storage cell. We'll just call this hybrids. Okay, capacitors, hybrids, and batteries. I'm really focusing on the capacitor side of things. I guess if I was going to put together a business plan, you'd have to look at it a little bit differently. The mass market might be electric vehicle storage, and then certainly you'd be considering batteries or some combination, possibly. But for the shade tree chemists and hobbyists, things are a lot simpler and lower cost to play in the capacitor sandbox, if you will. Capacitors, and we're really talking about supercapacitors here. So we'll just kind of relabel that as supercapacitors. And there you could either talk about a symmetric supercapacitor or an asymmetric. Asymmetric supercapacitor. Here, what we mean very simply is the anode and the cathode the same construction? Here, maybe there's a difference between the anode and the cathode, either in the chemistry or the construction. Remember, when we're talking about this type of energy cell, what we're really talking about are various components, and that's going to be part of the chart here in a minute, where we've got a positive terminal, we've got a current collector, we've got an electrode, we've got a separator, another electrode, another current collector for the minus side. And then somewhere in here, either as part of soaked into the separator or somehow soaked into the overall arrangement here, we've got an electrolyte. Basically a liquid that can allow for the ionic conduction within the cell and then the electron outside the cell. So symmetric and asymmetric. When we talk about symmetric cells, again, to keep it simple and low cost, I'm only going to be looking at those versions that are symmetric in terms of a carbon-carbon cell. What I mean there is the basic ingredient of both the anode and the cathode is carbon. So I call it a carbon-carbon cell, carbon on both the anode and the cathode. The next thing that we want to look at is, again, we talked about just briefly here, the components, the current collector, the electrode, the separator, another electrode, current collector. Let's break this project down into those individual components. If there were 10 of me, then I could spend all of my time developing the best current collector, developing the best electrode, developing the best separator, developing the best electrode, the best packaging, the best testing techniques, that sort of thing. But there's, since this is a hobby, there's one of me, and kind of narrow the focus down, keep this simple, keep this low cost, narrow the focus. Which one of these components or assembly or testing side of things can I dedicate my limited resources, basically time, to develop? So let's back this up a little bit and start talking about some of those component options. Okay, so the various components, again, of the storage cells that I'm looking at, in no particular order, consist of an electrolyte, and what type of electrolyte? Well, it could be a water-based or aqueous. It could be an ionic. It could be an organic. Lots of trade-offs here in terms of what's the least hazardous, what's the least expensive, which one might produce a higher voltage cell. So it doesn't necessarily mean that the safest, lowest cost aqueous are the best choice if you're really looking to push the cell voltage, north of 3 volts. You're probably looking at some of these. On the other hand, the compounds to do this are not available at a low cost to everyone, so there are some trade-offs. Maybe if I can make a 1.5, 1.8 volt aqueous cell, I'm already over my 3.5 volt organic cell if I just put 2 of these in series. Are 2 of them in series detriment? Well, if size and weight are not your primary goals, then maybe the aqueous is a better choice than the organic. But we're just listing things here. When we talk about an aqueous cell, I guess we could talk about those that are liquid, and anything from a solution such as sodium chloride, magnesium chloride, magnesium sulfate, potassium sulfate, zinc sulfate, potassium hydroxide. All of those could be liquids, and we could also fabricate them where maybe they're a little bit easier to handle, and we'll put them into a gel. Is there performance trade-offs here? Don't really know. Are there cost trade-offs? Maybe. But we've got a couple options here. So the path that I'm on is so far aqueous. Everything I've tested up to date is liquid, but we could certainly take a look at some of the gel options. Besides the electrolyte, another key component is the separator. The separator has to be able to pass ions, but not pass any of the compounds, molecules of the 2 electrodes. So common separators, at least for the experimenter, are things just like paper. Typically this could be copy paper, 1 or 2 sheets, and that progresses to where you can use some of the polymers. The commercial version that's used in your lithium ion batteries is a form of a naphthalene, which is a trademark name for a polymer separator. But for now, we're going to keep it simple and do paper. So far we said aqueous, liquid, and paper. In terms of the electrode options, here's where things get very diverse, if you will. In terms of electrode options, we've got many variations. I've already said that to keep things simple, I want to do a carbon cell. So the basic component here is carbon. But when we talk about carbons, there's many physical forms or allotrope forms of a carbon. And so far what we've done are looked at single carbons, a mixture of different carbons, different particle size, creating different pores for the ions to park, if you will. Trying to match pore size to ion size based on the electrolyte. A lot of interactions there. But we can either look at a single carbon, mixed carbons, or recently we've taken a look at some matrix or composites. So here we're looking at activated carbon, plus maybe throw in some graphite, and a common form of that is in a flake. And we're also looking at adding in a little carbon black to increase the conductivity. And if we want to get this mixture put together where we have good ionic flow and a lot of ion storage, we want to make sure that it's very porous and that there's a fair amount of the volume of it. I'm not really concerned about, as you would be if you were doing a high-end lithium battery, the number of grams of material used per kilowatt. Here we're basically looking at fairly low-cost materials, nothing exotic. So I'm really looking at maximizing the total energy storage, the milliwatt hours per cell. And one way to do that is to make a thicker electrode. But a thicker electrode is going to have issues with being able to absorb the electrolyte and the porosity. So we'll probably be looking at some type of a matrix or a composite. And I think in the next week or so we'll be doing a whole video looking at various ways to create a matrix by combining various carbons with a few other materials to get a lot of surface area and porosity and absorb the electrolyte. So more on that in a future video. After we talk about the electrodes, if you remember from my little diagram, we've got current collectors. Typically, an electrode may not have a low enough resistivity on its own to be its own current collector, but that would be the goal. The goal would be to eliminate the current collector and to stack up these cells, maybe in a bipolar arrangement where we have an electrode, a separator, an electrode, and that's one cell, and this electrode forms a portion of the next cell where we just keep adding separators and electrodes, separator and electrode. So here I've got 3 cells, 1, 2, 3, all in series, but I've only had to use 4 electrodes. And if these electrodes in the middle are low enough conductivity, then I don't need separate current collectors, maybe not even on the ends. But if there's some issues on the ends in terms of the packaging or looking for lower conductivity, then maybe I have to put some type of a current collector backing those electrodes. So in terms of current collectors, the goal is none, or zero. But if we had to look at something, and then we've got a lot of choices there as well in terms of aluminum foil or maybe a mesh. We get into some chemical reactions and plating out issues if we look at more active materials, particularly on the cathode. If we were to look at copper, maybe we could do a graphene to additive to get some much lower resistivity. But anyway, for the current collector, the goal here is to combine the current collector with the electrode and shoot for none. Okay, what's left here? I haven't talked about the packaging of the cell. I'm going to run out of board space here, but bear with me. If we talk about the packaging, are we going to make a wound cell like a lithium battery, just kind of a jelly roll? That's one way. A lot of issues there with the handling, at least if you're not in a production or a tooled setup where you can roll this up. Another arrangement would be a stack cell. If you look at what a number of people have done, even in the electric car space, for instance, they've gone to what's called a pouch cell, where something not unlike a polyethylene bag or pouch contains a stack. Well, let's say here's our pouch, and in that pouch we have an electrode / current collector and a separator and another electrode and another separator, and we can stack these up. Maybe it's one cell, maybe it's more than one. Okay, and the beauty of the pouch is that it's a low-cost way to contain the electrolyte. This is not a bag that's bulging, but if the electrolyte dries out or evaporates, your cell is gone. So at least on an experimental basis, we can build this up in a small pouch, and we'll include some of those details in our next video. But we can soak the separators and contain a little bit of electrolyte in this pouch to keep everything moist, and without too much trouble we can even seal it off, at least for an experimental duration, keep things from drying out. So in addition to rolls and pouches, and we talked a little bit about a bipolar arrangement, again we have a number of choices for the packaging side of things. The last thing briefly to talk about is testing. If we're going to develop and improve the cell design, whether it's the best electrolyte, the best electrode, the best current collector, we're going to have have a means to test the various options. And good test procedure says only change one thing at a time. I can't be changing the type of electrolyte I'm using and the size of the electrode and maybe whether I have 1 or 2 sheets of paper. I would have no idea if there was an improvement, what of those changes contribute to the improvement, and obviously if it failed, was everything good but maybe the separator. So change one thing at a time, control everything else. When I talk about control, the concentration of the electrolyte, maybe it's not optimized, but keep it constant. The area of the electrodes, we're talking about milliamp hours here in this cell, but it's really milliamp hours, let's say, per square centimeter of area. So define that area for the cell. Pick a constant. You'll see in one of my next videos, the constant that I picked is basically about a 1.5 by 2-inch electrode size. And why did I pick that? Well, it fit nicely in some little polyethylene bags or pouches that I had. But that's a good, reasonable size to look at improvements that you're making incrementally, one at a time. So anyway, that's my roadmap of where I'm at, where I'm going. I would love to look at all of the various options here for electrolytes and whether they're all liquids or gels, and the hundreds of various carbons that could probably be combined here to get the best porosity and the best surface area. But you got to pick your battles. And so far, just to summarize, we're going to be using something like a zinc sulfate and an aqueous electrolyte. Probably I'll stick for now with my 2 layers of copy paper for the separator. Don't get a lot of life out of this, but I'll get 10-20 cycles, at least enough to quantify things. And recently we've been playing with a composite or combination of carbons here. Again, fairly low cost, readily available. So that's where we're at on the roadmap, if you will, for energy storage. Thanks for watching, and please, as always, give me your feedback, your comments, your questions. As a group, I'm sure we can make more progress. With that, have a good day.